For this lesson, we will take a look at DR, digital radiography. This is not CR technology. CR plates capture a single image. The imaging plate is extracted from the cassette, read by the scanner, erased for reuse, and reloaded into a cassette. Additionally, the radiographer needs to have an individual CR cassette for each view of an exam, and the cassette needs to be marked with the patient information before it is scanned. A DR plate combines the actions of a CR system in a single piece of technology. The plate or array captures the image, reads the image, and sends the image to the computer and erases itself, ready for reuse. Since the capture array doesn't need to be loaded or unloaded before or during the examination, workflow is greatly enhanced. One word of caution: DR imaging plates are very expensive and can be irreparably damaged if dropped or mishandled. DR capture arrays are positioned in place of the Bucky tray or mounted inside of a Bucky, just like a film screen or CR-type cassette. Let's remove the tabletop and expose the DR capture array. All DR capture arrays are made of tiny radiation measuring blocks called Detector Elements, or DELs. Capture arrays will generally measure 7 by 17 or 14 by 17 inches in size. The illustration below represents an upper left corner of a capture array. The small squares represent the detector elements, or the DELs. The bordering items are contacts that query the detector elements and connect the DELs to the plate's electronics. Now let's take a look at a single detector element. The sensing portion of the element is lined in red, and the supporting electronics are outlined in green. The supporting elements consist of a capacitor to store the electron sensed by the DEL and a thin film transistor that acts as a gate, allowing the capacitor to release electrons when the DEL is read by the plate's electronics. There are two DR radiation measuring technologies in use today. The graphics below summarize the important elements of a single DEL. The top DEL uses a phosphor layer and a photocathode combination to measure the amount of radiation striking the DEL. This may be familiar to you, as it is similar to the first two layers of an image intensifier photomultiplier tube. The bottom uses an amorphous selenium semiconductor as measuring portion of the DEL. This technology was the basis of a 1960s-70s vintage form of mammography called zero radiography. For the top DEL, radiation strikes the phosphor layer and produces a flash of light. Since it diverges or spreads from the source, it may affect one or more DELs. To keep things simple, the light from this illustration will affect one DEL. Light strikes the photocathode and the electrons are produced by the photocathode. The electrons are stored in the DEL's capacitor, waiting to be read by activating the DEL's thin film transistor. The more radiation striking the DEL, the more electrons are released by the photocathode and subsequently stored in the DEL's capacitor. In the case of the bottom DEL, electrons are present in the DEL and can't migrate to the bottom of the DEL because an amorphous selenium semiconductor won't allow them to pass. When radiation strikes the semiconductor, it becomes conductive and the electrons can flow from the top of the DEL to the DEL's capacitor, awaiting to be read by the plate's electronics. And the number of electrons stored is proportional to the amount of radiation striking the DEL. Since the top illustration is a two-step process, it is designated as an indirect capture process. Radiation strikes the phosphor and the phosphor produces light. The amount of light produced is proportional to the amount of radiation striking the phosphor layer. The photocathode converts the light to electrons, and the electrons are collected in the DEL. Finally, the electrons are converted to electrical signal, and that signal is converted into a digital number and sent to the computer. The second process is called direct capture because an intermediate step of converting radiation to light is not necessary. In the top of the DEL, electrons are separated from the collector of the DEL by an amorphous selenium layer, which is a semiconductor. In its normal state, amorphous selenium is non-conductive. When struck with radiation, the amorphous selenium becomes conductive and the electrons migrate through the DEL to the storage electronics. The number of electrons that migrate are proportional to the amount of radiation striking the DEL. And as in the previous example, electrons are converted to an electrical signal, and that signal is turned into a digital number that represents the amount of radiation reaching the DEL. So now we have a detector plate made of millions of small detector elements which form pixels. Let's again zoom in on a single amorphous selenium detector element. And to this we'll add a computer and a communications line and a box that represents the analog to digital converter circuit. The job of this circuit is to take a signal produced by the DEL and turn it into a digital number. Let's expose the DEL to a different amount of radiation and see what happens. A small amount of radiation excites the amorphous selenium and causes the selenium to become conductive. So few electrons migrate to the DEL's storage capacitor. When queried by the plate's electronics, the electrons are sent to the analog to digital converter. Since the charge is small, the converter transforms the signal into a small digital number. The number is sent to the computer for display and storage. Compare this to a DEL exposed to a large amount of radiation. The detector is struck with a large amount of radiation, so many electrons migrate to the DEL storage capacitor, and then the DEL is queried by the plate's electronics. A large signal is sent to the AD converter, and a large digital number is produced. And as you may suppose, this number is sent to the computer. To briefly summarize, imaging plates consist of two basic types, direct capture and indirect capture. Indirect capture plates convert X-rays to light and then convert that light into electrons. Direct capture plate technologies eliminate the step of converting X-rays to light. Both systems send electrons on to the circuits which measure the electron charge, convert it to a number, and forward it to a computer. Imaging plates have a spatial resolution of 3 to 6 pixels per millimeter. This equates to about 1.4 to 5.5 million pixels on a 14 by 17 inch plate. At a given pixel pitch, indirect capture plates yield lower spatial resolution. This is because light from the phosphor layer can spread from its source and affect more than one DEL. Indirect capture plates do have a speed advantage over direct capture plates, so they can be used to produce multiple images in a very short period of time. Most DR plates I've seen find image on the plate and ignore pixels outside the collimated area, thereby conserving file size and limiting the amount of data needed to send back to the computer. It was soon determined that cassettes or cassette-like arrays could easily be retrofitted into existing equipment. Here is a picture of two choices. The cassette on the left is battery-powered and communicates with the computer using a radio link. The cassette on the right uses a cable to provide power and transmit data back to the computer. Since there are two basic methods imaging plates use to send data back to the computer, one must consider the following when making a purchase. For a tethered system, data is communicated back to the computer using a wire. This method is more difficult to adapt to existing X-ray tables because wires need to be installed or handled in the case of portable work. Data communication back to the computer may be faster and more reliable. Finally, power to run the plate can be supplied by the communications cable, so one doesn't need to worry about battery charge. Recently, wireless imaging plates have become available. Since there is no cable, these plates can be adapted to any existing X-ray table or situation without modification. Load the plate into the bucky tray and start work. Wireless plates are battery powered and attention must be paid to the state of battery charge. Usually one or more batteries can be recharging while another is in use. When purchasing a wireless system, it is important to pay attention to the number of images available per charge and the time necessary to charge a battery. Finally, can the plate retain an image or images if the signal back to the computer is interrupted? This is an important consideration. Thank you for your attention.